Hello, I'm Jacob Briggs, and I am here to talk about my binary search tree. So, first of all, um, binary search tree is a way to, well, it's best used to balance a set of data so that you can look through it in like half the time. Your goal is to have the middle be, or the root be around the middle so that you can either check left or right to find a value in the tree faster. At least that's my understanding of it. So first we make our node with a left and a right and a data so that we can keep track of all that. And then we have something here to make a new node. Some of the examples I looked at had this right here, so I looked into what this meant to see, hey, would this be cool to use? And pretty much what this function right here, or what this does, is it allocates enough memory to make the new node. I made a little note here for myself so that I can remember that's what this does, and yeah, and then so in that temporary, we put the data of the new node essentially, because temp is the new node that we're creating, as the number that we input in insert. Um, and then temp left equals temp right equals null, so that just checks to see if, or it makes it so that the left and right are null because we're not putting anything in to the left and right of the new node yet. And then it just returns. And then so this is, we'll come back to in order later, because what this does is it just goes through the list in order. So let's look at insert. So first it checks to see if the tree is empty, and if it is, it gives it a new node. Um, just as simple as that. It doesn't have to traverse anything if it's empty. And then if it isn't empty, then it checks if the data being inserted is less than the head of the tree. So it sees if the data is less than the node's data, which would be the head. And if it is, then it'll insert it into the left. It'll go as left as it can and plop it in there. And then if it's not less, then it'll check if it's greater. Um, and if it's greater, then it'll insert into the right instead of the left. It'll go as far right or left, right and then left. It'll find where it needs to go on the list. Min value is used later on. I did not put something here. My bad. I'm usually really good about commenting as I go. Um, so min value is used later on for, I believe I use it in delete. Well, we'll worry about that. And a max value is also used later. I guess I should talk about in order now. So what in order does is it makes sure, it always checks if it's not empty. If it's not empty, then it does go in, and it goes as left as it can, and it traverses forwards. It uh, it outputs what it finds, and then it goes to the right and does the same thing. Um, and so I think now I can show the first half of the show off. So I insert a root of 10 and insert 13, 5, 1, 20, 11, and 6. And so if I start this without debugging, inserting numbers now, displaying tree in order 1, 5, 6, 10, 11, 13, and 20. 1, 5, 6, 10, 11, 13, 20. So even though I inputted them not um, in order is able to go in and display them in the order that they need to be in. And then the next part of the thing, or the next part of the main, what it does. Oh, wait. Yeah, it does. Displaying current max number now, so I can talk about max number as well. So what max value is it starts at it makes current, which is our root, and then it goes to the right of our root as far as it can, and then it returns and outputs whatever is as far right as it possibly can be. And min value just does the opposite, but to the left. And what we also do after the system pauses, we delete 20 and 5, and then also show in order and max value again. So let's look at delete. So first, we check to make sure if it's empty, and if it's empty, then we leave. We're done. If the data is smaller than the root that is to the left, seek it and delete. Um, so it checks if the data that we're trying to delete is less than the roots, and then it goes to the left and deletes. It deletes it when it finds it there. And if it's greater, then it'll go to the right and do the same thing as up there. And then here, if the data is the same as the root, then it will be deleted. So this will handle changing what is the root if we're getting rid of the root. So here, these two right here will handle if the node has only one or no children on it. So this sees if left is null, and if it is, then it'll set the one to the right, or to the new root. And then this one just does the opposite. It checks if right is null, and if it is, then it changes the root to our left instead. And then this handles if the node has two children, find the smallest value in the right side of the tree. So what this does is, if we delete the root and it has ones on both sides, what it will do is it will find, because it's really weird how this works. I had to do a lot of research into how trees work and how the code works. But what you do is you find the lowest value on the right side, and that becomes your new root, because I think it's like the closest, I guess, to being what the root used to be. And then it messes with all the connections to make that work again. Uh, Binary search trees were kind of easy to get the structure of, but how it all like connects and how it needs to work was what was confusing. So anyway, so now the next part, after we unpause and go to the next one, it will delete 20 and 5. So it'll delete 20 and 5. It'll delete the highest number and second to the lowest number. And then it'll show it in order again, and it'll find a new max value. So let's continue. Deleting 20 and 5, displaying altered tree numbers in order now. So we now have 1, 6, 10, 11, and 13. We don't have 5 or 20 anymore. And the new max is now 13 instead of 20, because 13 would be the new highest number. And I guess that's it. Thank you.